Good afternoon, Shanghai, and good morning or good evening wherever else in the world you may be. My name is Rick Parker, and I have the honour to be the current president of ISABE, the International Society of Air-Breathing Engines. I want to share with you some of the highlights from our last conference. The conference is held every 2 years. It rotates around the 3 major continents. We met up in Canberra, Australia in September 2019. We were hosted by the University of New South Wales Canberra campus, and we gratefully acknowledge the support of all our sponsors, but especially the major sponsors shown here. This lecture considers a number of major themes emerging from the conference. The need for speed, both supersonic and hypersonic, has been dominant in our industry. Improving air travel remains important. There is much interest in future fuels, getting away from standard kerosene. Electric and non-electric aircraft are starting to emerge. And finally, I'll give you a tempting glimpse of what's to come in our 2022 conference. So throughout history of air-breathing engines, the push for greater and greater speed has been dominant. The last opportunity to fly supersonic as a paying passenger passed with the retirement of Concorde in 2003. NASA showed us their latest quiet supersonic demonstrator. This project is now well on with build at Lockheed Martin's facilities. Credit must go to Deputy Administrator Jae-won Shin, who drove this project through. It is vital to demonstrate that supersonic aircraft can generate an acceptable sonic signature at ground level. However, the propulsion system challenges do not stop there. The engine must meet existing noise targets for takeoff and landing. Supersonic aircraft engines cannot be modern high bypass engines, so we must deal with fan and jet noise of much smaller engines rotating at very high speed. This will require deeply embedded engines, similar to stealthy military configurations, with all the incipient problems of inlet distortion. There are a number of supersonic jet programs in progress. Once the flag is lifted to allow supersonic flight over land, especially in North America, the race will be on. Conditioning the air intake for supersonic jets is an important element of the engine design. Intake designs have changed relatively little since the original Concorde Olympus engines from Rolls-Royce 40 years ago. Speaking of the engine challenge, Korovkin and his colleagues from Siam in Russia showed us an alternative derivative engine with variable geometry. This engine study has a CFM56 engine at its core. They also showed a supersonic business aircraft concept, powered by their supersonic derivative engine. The very long nacelle helps absorb engine noise, while the variable mixer reduces takeoff noise. It lacks the very long profile shape of the NASA concept, so it's unlikely to achieve the sub 0.5 PSA boom at ground level that is required. America's latest supersonic military jet is the F-35 Lightning. It is powered by a Pratt & Whitney F135 engine, a derivative of the F119. This was described by Thomas Pratt of Pratt & Whitney. The alternative F136 engine from GE and Rolls-Royce was unfortunately shelved. Rolls-Royce does, however, produce the vertical lift system for the F-35C, the vertical takeoff version of the F-35 Lightning. This consists of a shaft-driven lift fan, dual fan, counter-rotating, driven by a shaft off the main engine through a carbon clutch and gearbox. At the back end is a 3-bearing swivel nozzle, which can transition from horizontal to vertical flight in just 3 seconds. At speeds significantly beyond Mach 2, we're into the hypersonic regime. which brings its own propulsion challenges. Kevin Bowcutt of Boeing gave an excellent introduction to the hypersonic flight, based on his long experience in the field. Here are some of his rules of thumb. Conventional turbines will get you to around Mach 4.5, but have the advantage that they work from zero forward velocity, unlike ramjets and scramjets. Australia is a major centre for hypersonic propulsion research, and 5 universities all work together in developing these technologies. NASA has signed a new collaboration agreement to use the research institutes and the Woomera testing range to further develop hypersonic propulsion in partnership. The Boeing X-51 Waverider is an unmanned research scramjet for hypersonic flight at Mach 5 and an altitude of 70,000 feet, that's 21,000 meters. It completed its first powered hypersonic flight on the 26th of May 2010. On the 1st of May 2013, it completed a flight of over 6 minutes and reached speeds of Mach 5 for 210 seconds. This is the fastest and longest duration powered hypersonic flight of this type. Similar to its Boeing counterpart, the Chinese are already driving forward in hypersonic propulsion systems with their 0901. There were several projects in the 1980s to create a hypersonic passenger aircraft. The American HST and the UK HOTOL were just 2 of these. All were unfortunately shelved. More recently, Boeing has relaunched its ambition with their Mach 5 hypersonic transport concept, shown here. We also heard from Adam Dissel, president of Reaction Engines Inc. The company Reaction Engines was the brainchild of Alan Bond. I worked with Alan on the original UK HOTOL spaceplane engines in 1985. HOTOL used the liquid hydrogen fuel to cool the incoming air. Several miles of fine titanium tubes filled with liquid hydrogen was not such a great idea. The latest ISABE concept from Reaction Engines introduces a liquid helium cycle as the inlet cooling medium. The helium boil-off in turn preheats the liquid hydrogen and drives the hydrogen fuel pump. The inlet air cooler has been demonstrated under an ARPA grant in the USA, running in the exhaust stream of a GE military engine, where it demonstrated the ability to drop the inlet air temperature by 250 degrees C. The unique Sabre engine operates as a conventional turbine at low speed, less than Mach 4, and then switches to rocket mode at high speed, burning its liquid hydrogen in pure oxygen. Here's a photograph of the DARPA-funded pre-cooler test. You can see the pre-cooler on the right. It's over 1 meter in diameter. And on the left, through that panel in the wall, is the GE jet engine, which is providing the hot gas for the pre-cooler. More scramjet work was described by Maritano from Tohoku University in Japan. Their Modkey hydrogen-powered test model is mounted on the ceiling of the Heist test section with 2 electromagnets. When the electromagnets are deactivated, the model was dropped 400 milliseconds just before the test flow arrived, so it was in the center line of the test section. Then the engine ignites. Pressure and acceleration histories were recorded during free flight. Finally, the model was landed on the shock-absorbing system on the floor of the test section without any damage to either. Pretty neat. Alex Ward and Mike Smart from the University of Queensland described some novel aerodynamic modelling of a hypersonic vehicle. I think you'll all agree that the results for the vehicle at Mach 8 are rather beautiful. Professor Michael Smart went on in his keynote to propose the use of the same hypersonic scramjet as part of an affordable satellite launch system. You can see the details of that system described in the list below. His novel concept for a three-stage to-orbit system is based on a reusable rocket, a scramjet, and a disposable final stage rocket. The reusability of the first two stages and the ability to navigate back to the point of takeoff gives it an advantage over other competing systems. He's established a company, Hypersonic, to develop the system further. One of the major factors driving commercial air travel is concern for the environment. The industry has committed to impressive targets to reduce CO2, NOx, and noise emissions by 2050. The ultimate plan being to arrive at net zero carbon air travel. We had a fascinating talk from Captain Alex Passerini, the chief test pilot at Qantas. Although ISABE is an engine society, we like to get views and input from all parts of the industry, especially the end users. Qantas had just launched their new Kangaroo route using their 787 Dreamliner. This is the first non-stop commercial flight from Australia to London. There is a wise saying that no sane person should fly more than halfway around the world. The map also shows the early experience of commercial travellers who had to use flying boats, when the journey took 4 days with 6 stops on the way. Perversely, if we did the same route as the flying boats with modern aircraft designed for short range with highly efficient engines, we'd probably do less damage to the environment than a single long journey, when most of the fuel carried by the aircraft is carrying fuel rather than carrying people. We also heard from Paul Stein, he's the CTO of Rolls-Royce, about the efforts to push gas turbine efficiency and performance to the limits. To do this, you have to extract the maximum thermal energy through internal aerodynamic efficiencies and higher pressure ratios. And you have to maximize propulsive efficiency. That's the efficiency with which power from the engines is translated into thrust to the aircraft. This implies a very high bypass ratio. Rolls-Royce's UltraFan pushes propulsion efficiency even further and combines their 3-shaft novel engine with a new low-pressure, low-speed fan. The fan is separated from its driving LP turbine by a high power density power gearbox, allowing the turbine to maintain a high speed and high efficiency. The gearbox for the UltraFan is a novel design generated by Rolls-Royce with its partner Liebherr. The target efficiency for the gearbox is over 99.5%. But even at this efficiency, the remaining loss will manifest itself as heat, and 375 kilowatts has to be dissipated somewhere through the oil system. Testing has successfully demonstrated this gearbox at a novel test facility outside Berlin, both in level flight and severe inclination conditions. One of the other concerns for global warming is contrails from aircraft. Sébastien Cantin and colleagues from the University of Quebec showed their approach to modelling contrails. The approach combines CFD for plume tracking with embedded particle tracking. A microphysics module and SAR CCM Plus code populates the model with ice particle properties and particularly the size distribution of the ice particles. Noise is another aircraft impact to be minimised. NASA has set a long-term noise goal of 42 to 52 dB cumulative below stage 4. Van Zanti from NASA described their latest thoughts on airframe engine integration on various concept aircraft. They took as an example the NASA D8 concept, shown at the top left, with rear-mounted engines for boundary layer ingestion and noise shielding, and also the NASA Star-C AB concept, with rear fan for boundary layer ingestion and re-energization. In these configurations, the modelling must take account of effects of inlet distortion, jet surface interaction, reflections of jet noise and rearward fan noise from other surfaces. In both these cases, the noise benefits were shown not to be as high as originally expected. Increasing thought is being given to future fuels to enable zero carbon. Biojet fuels are not generally carbon neutral and today are only permitted in a maximum 50% blend. Synthetic aviation fuel can be carbon neutral but not zero carbon. It's made from captured CO2 and green hydrogen. The CO2 released into the upper atmosphere has a higher warming effect than that originally captured at ground level. Hydrogen is the only real zero carbon fuel for the future, but may cause higher NOx if combusted. It may also release of order of 10 times the water vapour compared to burning kerosene. This may lead to increased concerns over contrails and cirrus cloud. So basically, there's no free lunch. In this table, I compare kerosene Jet A with other fuels for a return flight from London to New York. In terms of weight of fuel, hydrogen has an advantage over kerosene. However, it must be stored in heavy cryogenic fuel tanks. When converted to electricity in a fuel cell, hydrogen looks even better, but a fuel cell is much heavier than a gas turbine. Hydrogen loses out in volumetric efficiency, requiring larger tanks and bigger aircraft for the same range. Just for fun, I've included uranium. Nuclear aircraft look quite promising. Just 18 grams of fuel for a return journey to New York. Not bad, really. This nice cartoon from NASA epitomizes the challenge for all electric large aircraft. It possibly can be done, but leaving no room for passengers or payload. So let's look further at electric and hybrid propulsion. If all electric propulsion does take off, we may need to change the name of our society, since engines will no longer be air-breathing. For this electrical journey to be successful, all aspects of the electrical system require a factor of 2, ideally a factor of 10 increase in power or energy density. The most challenging of these is probably the battery technology. Physics and chemistry are likely to set ultimate limits of around 1 kilowatt-hour per kilogram, which is only 4 times better than the best today. Every part of the system must be minimized in weight. That includes the cabling, and novel systems may allow significant and disruptive improvements in this. Ralph Jensen from NASA Glenn described their propulsive fuselage concept. This is an engine maker's dream. So many propulsion units on one aircraft. Wow. This hybrid electric aircraft has conventional engines for primary thrust and electrical power generation. An array of electric fans around the rear of the fuselage ingest and re-energize this boundary layer. The large number of fans ensures maximum boundary layer coverage. Further work on the propulsive fuselage was described by Trosch and his colleagues from Bauhaus. This was done under the EC Centerline Consortium. You can see the large number of members of the consortium at the bottom of the screen. A series of trade studies was reported for rear fan boundary layer ingestion configuration. The optimum figure of merit led to a 5% total cruise drag reduction. This is similar to the drag reduction seen in other studies on boundary layer ingestion and is well worth having. Another study from the Centerline team, led this time by Sebastian Samuelsson, looked at optimizing the main turbofan for this hybrid solution. Compared to a conventional geared turbofan engine for the same size aircraft, less thrust is needed from the main engines, some being provided by the rear fan. However, higher mechanical power offtake has to be extracted to drive the generators, and these generators themselves will be very large in this configuration. Even luxury car maker Aston Martin is getting in on the act with its Volante concept, powered by Rolls-Royce electrical systems. Do you think this could be in the next James Bond movie? Let's wait and see. ISABE 2019 seems a long time ago now, so I thought I would finish with a teaser for our 2022 conference. We will publish this month a special edition of the Royal Aeronautical Society Journal. Before we took the decision to postpone our conference in 2021 until 2022, we'd already received a lot of abstracts and papers. We selected 11 of these, and these will be published this month in the Royal Aeronautical Society Journal. From Jeonbuk University in Korea, Choi and his colleagues demonstrate the effect of using a lobe mixer on exhaust infrared signature at various bypass ratios. At bypass ratios over 1, it creates a significant reduction compared to a plain conical nozzle. This may be increasingly important as commercial aircraft come under threat of rocket attack from terrorists. One of the concerns for synthetic and biofuels is that we don't fully understand the effects of aromatics in kerosene today. On the left, you see a detailed study by an international team from America, USA and Russia, who looked at various fuels and levels of aromatics with typical fuel seal materials. They used fluorosilicone and nitrile O-rings. It will hopefully help producers ensure that future bio and synthetic fuels are truly drop-in fuels and do not have adverse effects on engine components. Meanwhile, on the right, Yang and colleagues from Xi'an Jiaotong University have done some elegant modelling on deposition of ash on turbine blades, correlated with particle size. This will help to understand turbine blocking and lifing. This is especially important, as we've seen in recent years, in the event of volcanic eruptions. On the left, Li Longjiang from the National Research Council of Canada shows an elegant alternative approach to fuel air mixing modelling. This is based on fuel air equivalence ratio distribution, and in this case looked at a simple methane air Venturi mixer. Unlike traditional approaches which are based on unmixedness parameter and uniformity index, it is directly correlated with the mixture combustion properties and hence both quicker and more useful. On the right, in another fuel-related paper, Zhu and his colleagues from AECC Shenyang Engine Research Institute in China looked at modelling under realistic engine conditions of fuel jet trajectory and breakup behaviour in crossflow, with excellent correlation to published physical observations. Some rather nice pictures, I think. Finally, back to electrification and alternative fuels. On the left, in a study similar to those we saw in the previous conference, Ibrahim and colleagues from Cranfield University did more detailed work on the hybrid rear fan boundary layer ingestion concept. This time they're looking at some of the electrical system implications for aircraft integration. On the right, in another paper from Cranfield, Huerta and colleagues did some fascinating work modifying an A380 to create a medium-range hydrogen-powered twin-jet. They made full use of the vast fuselage of the A380 for hydrogen fuel tanks and studied 3 different configurations. Because of the lower passenger load and lower fuel weight for hydrogen, they were able to use A350 wings with the A380 body. Could this be the future for hydrogen flight? Let's wait and see. I hope that's given you just a taste of what's to come at our 2022 conference. We look forward to seeing many of you in Ottawa in September next year. And if this has stimulated your creative processes, it may not be too late to sneak in an abstract. Look at our website. Thank you all very much for your attention. I'll be happy to take your questions, assuming I've left enough time. For further information, please refer to the ISABE website, where you'll find all the papers from our previous conference, a detailed program for that conference, and also news about the future conference. The papers from the Royal Aeronautical Society Journal will be published by the Society in its journal sometime later this month. Thank you all very much.